So we're continuing here with our discussion around vertical slices and horizontal slices. And our goal is to evaluate the following double integral. So we've got the integral from 0 to 4, integral from y over 2 to 2, what we're trying to integrate, y e to the x cubed, dx dy. Well, if we look at the inside differential here, inside differential is dx, so that tells us that we're supposed to integrate with respect to x first. But let's observe that we can't integrate something like e to the x cubed with respect to x. See, in order to even try to integrate this, you'd probably do a substitution where you let u equal x cubed, but then you wouldn't be able to find your du. So long story short, that substitution would not work. We can't integrate something like e to the x cubed or e to the x squared without some other factor beside it to help us with our substitution process. But now that we've had a discussion about vertical and horizontal slices, there are some other tools that we could draw upon. So what we could do is actually sketch the region R, and we could swap the order of integration. Because right now this problem is set up with the order dx dy, which means it was set up using horizontal slices. But if we draw a region R and we reimagine this using vertical slices, it's possible that the actual integration process will become easier. Okay, so let's draw a picture and see what's happening here. So we're talking region R in the xy plane. Just from looking at our double integral up here, we can say our x values are ranging between y over 2 and 2. We know that the x values are on the inside integral because dx is the inside differential. And then we know that because dy is on the outside here, we know that the y values are going from 0 to 4. Okay, so let's see if we can sketch this. We would need to draw a picture of the line x equal y over 2. That's forming the left endpoint of our horizontal slice. If we just do a little bit of algebra here, solve that for y, x equal y over 2 is the same thing as y equal 2x. Okay, so let's start to sketch this. Let's go up maybe a few units in the y direction, a couple units in the x direction. So y equal 2x looks like that. Okay, and we're saying that these horizontal slices are going from that line. They're going over to x equal 2. So x equal 2 is going to be an important line to have on here. X equal 2 is just a vertical line, so I'll draw that in blue. Here's our x equal 2. And then let's think about what y values we're capturing in this region. So we're going from 0 to 4. Okay, so let's put a y value on there. And that way I think we can describe our region now. So we're saying each horizontal slice is going from this line x equal y over 2, which we decided was y equal 2x. So it's going from here all the way over to x equal 2, like that. So all of our horizontal slices are doing that. And for what y values are they doing that? Well, they're doing that for y values from 0 to 4. So if we just map out our entire region R, it's that entire triangle there, formed by the lines y equal 2x, formed by the x equal 2, and then formed by the x-axis here, which is y equals 0, if we wanted to think of that in terms of an equation. Okay, so right now, this has been set up using horizontal slices. We know that because we talked about x values first and then y values. So let's see if we can re-describe the same region here, but doing vertical slices. So this is still the exact same region R. If we want, we could label this region up here, call that R. Still the same region, but just described in a different way. So we want to think about y values first and then x values when it comes to vertical slices. Okay, so let's draw some vertical slices. And so all the vertical slices no matter where they are in that region, would have y equals 0 as the bottom, y equal 2x as the top. So y value is going from 0 to 2x. Fortunately, no need to split this into two different regions because we've got that consistency where every vertical slice has the same line forming the bottom and the same line forming the top. Okay, and then just casting a quick glance over our region, the x values are going from x equals 0 to x equal 2. So that gives us our limits of integration if we were to reimagine this using vertical slices. All right, so I'm going to write down the integral that we were given in the problem. So it's the double integral from 0 to 4, from y over 2 to 2, y e to the x cubed, dx dy. So we're going to rewrite this using our vertical slices. The integrand is not going to change at all. So it's still going to be y e to the x cubed. The dy dx is reversing. So dy dx now for vertical slices. Y values go on the inside. They're going from 0 to 2x, and our x values are going from 0 to 2. Okay, so this has been rewritten using using vertical slices now. The value of the integral is exactly the same, because really all we're doing here is we're summing up these values of y e to the x cubed times this little dx dy for all the x and y values over that region. So whether we run through all the points x, y by horizontal slices or whether we do it for vertical slices, we're getting the same value for the double integral. But we've now created a situation where the integration is possible. Cool, huh? So let's try our integration. We'll see how nicely this goes. We're going to integrate with respect to y first. We always do our inside integral first. X is just held constant. So we're going to write down our outside integral, write down our outside differential, and let's integrate with respect to y. So the y would become y squared over 2. And the e to the x cubed, just a constant. This needs to get evaluated at y equal 2x, and then y equal 0. So next step, let's do our evaluation. Keep the outside integral on there, keep the outside differential on there, and let's evaluate. So if we go y equal 2x, if we square that, we get 4x squared, but then that's divided by 2. So I'm going to call that 2x squared times e to the x cubed. And then when we subtract off the value at y equals 0, well, that's just going to be 0. So you could say minus 0 if you wanted. But since that's just 0, I would probably be inclined to not even write that part down, and then I wouldn't need the brackets. Okay, so now it comes down to integrating 2x squared times e to the x cubed dx. And the reason this is going to work so well is that we're going to do a substitution here, and this 2x squared is going to help us create our du. So the substitution will go smoothly this time. All right, so whenever we see an exponential in the integral, particularly if you have an exponential, times something that looks like the derivative of what's in the exponent, the exponential, then substituting u equal the exponent is going to be a good way to go. So let's let u equal x cubed. Du would be 3x squared dx. And we'd say, well, if we look at this integral here, we don't quite have 3x squared dx. We have 2x squared dx. So the way we're going to move from 3x squared dx to 2x squared dx is we're just going to take 2/3 of du. So 2/3 of du is the same thing as 2x squared dx. Great, so that's our substitution process done. Let's go up to our integral, and we'll get this in terms of u. Okay, so this is going to be the integral from, I'm just going to write x equals 0, x equal 2, and what we're integrating now, e to the u times 2/3 du. Okay, so integral of e to the u with respect to u is e to the u. So we're going to have 2/3 e to the u. I'm just going to evaluate at x equal 2 and x equals 0. So in order to evaluate, we need to get this back in terms of x. Remember that u was x cubed. So we get 2/3 of x cubed, and then we're just going to evaluate at 2 and at 0. Okay, so we can factor out that 2/3 because that's going to come up in both parts of our answer. Subbing in the 2, we'd have e to the 8. And then we're going to subtract off what we'd have at 0, while e to the 0 would be 1. So our answer is 2/3 times e to the 8 minus 1. So this example, I think, really highlights the power of being able to switch between vertical and horizontal slices, because what we had in this problem was this integral here that was imagined using horizontal slices, and the integration was not possible. So we reimagined it using vertical slices. And because that changed the limits of integration, and it changed the order of integration, that gave us a double integral that was actually fairly easy to compute.